for the first session. So for the first session, will be taken by Rani Purohit, madam. So, madam, you please start. Okay.
Yes, sir. Yes, sir. Yes,
Okay.
sir.
Okay.
Good morning, everyone. I'm Pranati Purohit. I'm going to present on the topic. The topic is artificial intelligence and machine learning based controllers design and their application real time platform. In this workshop, I'm going to present a topic on inverter control of bidirectional converter with PV system and islanded and grid connected mode. The contents are introduction, then literature review, then motivation, objectives, system configuration and design, result and discussion, conclusion, and then my references. Now, coming to the introduction, renewable energy sources are, as we know that we are tremendously with expansion of renewable energy resources due to the known reasons known to everybody. So among the solar renewable energy resources, solar photovoltaic and wind energy are very much prominent in nature. That is, it is mostly used in many of the
வெறும்
countries.
கெப்பாசிட்டர் அண்ட் ஸ்விட்ச் அது பி பசங்க பண்ணதா இருக்குமோ
PV and wind energy production are intermittent in nature. Therefore, we need a battery energy storage system to reduce this constraint. Thus, we can form a hybrid microgrid also. Besides this battery energy storage system, we have different supercapacitors, different energy storage systems also, but I have considered only battery energy storage system. Then a suitable so when PV, wind, or any of the renewable energy resources are connected along with the storage system, we need to have a control strategy to regulate the voltage and frequency and sustain power equilibrium among the different units and also to fulfill the load demands. Now, considering the intermittent nature of solar and wind power generation, battery energy systems rated power and state of charge also are considered. And also inverter capacity. I have designed for 1 kilowatt of inverter. Then these are my literature survey. So in the microgrid, lot of work has been done. Different controllers are used on the DC side as well on the AC side. So we have a DC bus, we have a AC bus. In the DC side, you have your DC sources connected, and then it goes to the AC bus through an inverter. Now, for that, the different control strategies are including the PI controller, sliding mode controller, and fuzzy logic controller, H infinite controller. Different control strategies are used. So this is a basic review of like a sliding mode control based on PV wind based DC microgrid with battery energy storage is proposed in this particular reference. You can go through the different references to have different control strategies. Then coming to this one, we have droop control also. So depending on our frequency and voltage, we have the mathematical representation and the PI. And main thing is that we have to find out the proportional and the integral error in the PI controller tunings. Similarly, and basically it's a trial and error method. Similarly, we have different algorithms or different control strategies because of which different optimization techniques are also used to find out the parameters. So basic literature review is regarding this one, and it shows a review of the fuzzy logic controller also. Because fuzzy logic is fuzzy logic controller doesn't depend on the mathematical model. That is why it is used in plenty throughout this for this microgrid control. So these are some of the advantages of the fuzzy logic controllers mentioned in different research papers. Then coming to the motivation, the introduction of different load and generation, voltage fluctuation, and stability difficulties can affect our transient and dynamic response of the microgrid. Therefore, the voltage and frequency should be enhanced while we are using nonlinear load, balanced load, unbalanced load. Therefore, this is a challenging task how to how to equip all the equip or adjust the controller, how to control the voltage and frequency in a microgrid. Now, to balance, therefore, a different control strategy needs to be developed properly to balance the generation and demand. Battery energy storage is required, and as we all know, due to the intermittent nature, that is renewable energy. Sometimes during the day and during the night time, we do not have renewable energy sources. During the cloudy seasons, we do not have the access to this PV sources, and at different times we have this wind energy produced. So due to this intermittent nature, to balance the generation and demand, we need to have some storage system. Here I have considered battery energy storage system. Sorry. A suitable control strategy needs to be developed for the bidirectional converter. Now, when we have the battery energy storage system, we need to have a bidirectional converter which can work either as a buck mode or as a boost mode depending on the application that we can see through while going through this PPT and our simulation. Now, for this all intermittent nature and to equip the battery energy system with the bidirectional converter, as well as we need to have AC loads with the inverter. Therefore, our develop a robust control strategy needs to be developed so as to achieve the good performance parameters. Now, again, the control strategy needs optimization techniques to find out the parameters of the controller. So, the motivation of this work is to find out a suitable control strategy and an optimization technique to find out the parameters. Then, objectives. Because of those motivations, my objective is to define and develop a suitable controller with appropriate optimization technique to manage the power effectively in a microgrid. And the control strategy should operate the bidirectional converter. Now, in the system design, configuration and design of a PV system connected to DC bus and design of a PV system connected to AC grid. I have considered for the DC bus and also for the AC side. Now, when the design of a PV system connected to DC bus, we have or I have considered 2 points. One is design of a PV system and battery with bidirectional converter, then bidirectional buck boost converter model. Design of a PV system connected to AC grid. There we have studied design of a grid connected inverter and implementation of physiologic controller in the inverter control. Now, because of the simplicity, I have avoided the modeling equations because it is plentifully available in the literature. What we are going to see is the working of this one and the concept behind it. How does the simulation work? Now, coming to design of a PV system connected to DC bus. So here we have a PV system and a battery with bidirectional converter. This is our PV system, which has irradiance and temperature. Irradiance is generally 1000 watts per meter square in our literature, or with varying irradiance also. Many research papers have considered. Here I have considered both at 1000 watt per meter square and varying irradiance also. Accordingly, we will see the plots. Then we have used the MPPT algorithm. It needs maximum power point tracking algorithm, which uses the particle swarm optimization. Again, we have different algorithms for the MPPT, say perturbed absorb, incremental conductance method, and now ANN also has come, fuzzy logic also has come. For the MPPT, different control strategies, different algorithms are developed. I think you had attended in earlier sessions different algorithms of MPPT control, then which goes to the PWM of the boost converter. Here I have considered one boost converter. This carries our resistance and our transistor, then our diode, then we have our inductor, then we have the battery sources. And this follows through a capacitor and a different load is connected. We can use here IGB presentation of the PV system with battery storage. Now I have considered here 1 kilowatt of PV array linked. Sorry, it is inked. It is by mistake typed inked. It is linked to the DC bus with via a DC-DC boost converter with MPPT. This is our battery connected to our PV system with a boost converter and a bidirectional converter. Here I have considered 24 ampere hour lithium ion battery interfaced with a DC grid via a bidirectional DC-DC converter. Now, the rated voltage of the DC-DC converter is 70 volt, which comes from the MPPT algorithm. First, we need to check here what is the DC bus voltage coming here at this point. Okay. Then we need to give the reference accordingly. I'll show you in the simulation while doing this one how to keep it at 70 voltage. This is not randomly taken. We have to measure the voltage across this one. Then we have to keep the rated voltage fixed, DC voltage. Then design of a PV system connected to DC bus. Now here we have this control algorithm. A control structure of the bidirectional DC-DC converter says that we have the DC voltage reference here and the measured DC voltage, which are passed through a PI controller. Now the difference between the DC voltage reference and the measured DC voltage. Here the DC voltage reference is 70 volt, is measured and the error is passed through a PI controller where the current is the output and the I battery reference. This is reference of the battery current comes out of this PI controller, which is compared with the battery current, and the error is again passed through another PI controller. And this is for the pulse width modulation, which is compared with the triangular wave. Then which is if it is greater than or equal to, and now two switches are there, Q1 and Q2. As we have seen our earlier, Q1 is a switch, Q2 is a switch. These two Q1 and Q2 switches. Now when VDC is greater than VDC reference, greater than or equal to, it will go to Q1. If not, then it will go to Q2. This is the control logic used here. Now battery control loop scheme, it comprises of two loops. As we have seen, this is our inner loop and it is current control loop. You can see the mouse pointer. It is a current control loop which regulates the battery current in response to the fluctuations of the parameters. Then this is the outer voltage control loop. VDC reference is compared with the VDC, which forms the outer voltage reference. Then the design of a PV system connected to DC bus once again has bidirectional buck boost converter. As we have seen, DC-DC converter, it sustains continuous power flow between the DC bus and the battery energy storage system while maintaining a constant DC link voltage. Here we have used the constant DC link voltage of 70 volt. Now, regardless of whether the battery is charging or discharging, see, we have different irradiance conditions. If we have higher irradiance, say 1000 watt per meter square, then the control logic is such that it will charge the battery. But whereas if the irradiance goes below 500, say around 300 watt per meter square, that is the battery cannot be charged. Rather, whatever energy stored in the battery when the irradiance was 1000 watt per meter square, that battery charging, the battery will start discharging for the load. So we have to maintain in any of the conditions, let it be charging, let it be discharging, we have to maintain a constant DC link voltage. Now the reference DC link voltage for, as I have mentioned, it is 70 volt in this paper research. Now, VDC is the DC link voltage. These are the different terminologies used. VDC is the DC link voltage. VDC reference is the reference voltage. I battery reference is the reference battery current. I battery is the measured battery current. Now, Q1 and Q2 are the switches which operate in complementary mode, either buck mode or boost mode. It can be switched here Q1 or Q2. Any one of the switches will operate at a time. Then design of PV system and battery with bidirectional converter. We can see from the control logic that VDC is greater than VDC reference, then Q1 will operate the circuit as a buck converter. See here we have mentioned VDC is, if VDC is greater than VDC reference, then Q1 switch will be connected and it will operate it as a buck converter. Then similarly, when VDC is less than VDC reference, you can see here when if not, here the not logic is used. That is, if VDC is less than VDC reference, then Q2 switch will be used, which will operate it as a boost converter. Now VDC is compared with the VDC reference to provide the error signal, which is processed through the PI controller. I battery is compared with the battery reference is compared with the I battery to derive the error signal, which is processed through a PI controller to provide a PWM signal. Now the PWM signal is compared with a high frequency triangular signal to generate the switching pulses. Switching pulses of this DC-DC converter, that is switching frequency, I have used here in this reaches as 5 kilohertz. Then the parameters of the PI controller for the voltage and current control loop are stated here. These two parameters KP and KI values I have used by using this trial and error method, and I have used particle swarm optimization method to find out the KP and KI. Then the bidirectional buck boost converter model. In this present strategy, this is our load, capacitor, Q1 and Q2 switches, inductor, then we have the battery. To approximate the converter to the continuous time, nonlinear time invariant system, state space, here we have used state space averaging applied to respective time periods of both subintervals. Now to obtain a linear system which is continuous in time and time invariant, the nonlinear system is
என்ன ஆகுதுன்னு பாத்துடலாம். அவரு இது பண்ண வேண்டாம்னு நினைக்கிறேன். பாத்துக்கலாம்.
The nonlinear system is first linearized around the operating point. Now the transfer function can be represented as follows. See, we can see from this one, this block diagram. Are please, could you please turn off your mic? Could you please turn off your mic? Now the transfer function is IL cap divided by D cap in S domain. This is the BDC is the DC bus voltage. ZDC is this one, load. CDC is the capacitor plus VDC 1 minus D. D represents the duty cycle. This is ZDC multiplied by IL. We can see this one from the next block diagram. Now this is inductor value. CDC, ZDC, S square plus LS. L is the inductor in S domain plus 1 minus D square. We can, in some research papers, it is mentioned as D dash also. Okay. Now this is ZDC. Similarly, we can find out VDC cap divided by IL cap in the S domain. This is equal to, as seen in the expression, ZDC, VDC multiplied by 1 minus D. D is the duty cycle minus L is this inductance value, ZDC, ILS divided by VDC, ZDC, CDC in the S domain. Okay, plus VDC plus 1 minus D, ZDC, IL. You can go through this expression, and this expression you can find out different in different research papers also. This transfer function is designed when you are considering the different design configuration of the bidirectional buck boost converter. You need this transfer function. So this is the BDC is the output. Here this is VDC reference voltage. The difference of these two are passed, and these are the different transfer functions. PWM. PWM is generally 1. Okay. This is the inner current control loop. This is the outer voltage control loop. This is one, as you see the pointer, this is the inner current control loop. We'll see the beta I and beta B are the sensor gains. Beta I is called as the current sensor gain and beta V is the voltage sensor gain. This is current loop control loop gain. This is voltage control loop gain. This instead of this transfer function, I have written this one. Then after substituting all the transfer functions, we can obtain the inner current control loop and the outer voltage control loop. Then design of a PV system connected to AC grid. Here we have used delivering a sinusoidal current to the grid and complying with international standards are virtual features or vital features of a high quality power inverter built for grid connection. Fuzzy logic control method is used to regulate grid connected three-phase inverter system with good performance. We can use it for the single phase inverter also. Now fuzzy controller comprises 3 fundamental elements. Many of you might have done research in the fuzzy logic controllers. So you might be aware of this one: input fuzzification mechanism, inference engine, which is the rule estimation, then output defuzzification mechanism. Now input variables are this input, first it fuzzifies the given variables. Now the input variables are current error and change in error. Then the output variable, which is defuzzified, is the duty cycle. Now I have used the maximum minimum composition reasoning method proposed by Mamdani. And Tekage-Suzino fuzzy is also another advanced method which is used in this microgrid control. Design of a PV system connected to AC grid. Now in the AC side, this is the inverter control current connected. This is the PV array which gives the MPPT, that is which tracks the maximum power point tracking method. Then this is the L filter I have used here. We have L, LC and LCL, different kinds of filters used, which is connected to the grid, and it is passed through a controller, this control logic, which provides the switching pulses to this inverter. Now it uses a fuzzy logic regulated control loop to manage the grid active and reactive current components ID and IQ. By controlling this active and reactive current components, we can control this active and reactive power also. Now, generally, this if we want to achieve unity power factor, our Q-axis component is set to 0. Now, ABC coordinates we have, say, I have here, I will show in the while telling you the diagram. Now, it gives unity power factor operation. That is, voltage and current are in phase with each other. Voltage and the injector current, which is synchronized with grid voltage. Here I have considered for the ease of the simulation, as I am using a 3-phase inverter of 50 kilowatt of PV connected to the grid. Then the implementation of fuzzy logic controller in the inverter control. ID is the different nomenclatures. This is ID is the direct axis current, IQ is the quadrature axis current, ID star is the reference value of the direct axis current, IQ star is the reference quadrature axis current. And the discrimination in currents along the DQ frame is the error in the current, which is further supplied to the fuzzy logic error for error minimization. Here minimization is omitted. We can explain it in this control diagram. Before that, the subsequently generated values from the two fuzzy logic controllers are transferred into the ABC coordinates. Now current is controlled and injected into this grid. Therefore, it is known as a current control scheme. In this control, we are controlling the current injected into this grid. This is the current injected into the grid. Therefore, it is called as a current control scheme. Now, implementation of fuzzy logic controller in the inverter control. So, if we come to this diagram, this is a PV array which has different irradiances and which works at different temperatures. Then this is a capacitor to stabilize this bus voltage, then which goes through an inverter. Inverter which has 6 switches, as I have used a 3-phase inverter. This is the current sensor. These 3 are the current sensors which senses the current of the 3 phases I, A, B, C. Now I, A, B, C are the currents in the ABC coordinate. Therefore, to simplify, we have to convert or we have to work with the direct and the quadrature axis, which are the DC values. It is easier when we convert this ABC coordinate to DQ0 transformation. Therefore, we need to work only with the DC values. Therefore, the respective currents on the ABC frame are transformed into DQ0 transformation, which further produces ID and IQ. Now, this is omega T. Omega T. Now, this is a voltage sensor. Now, ABC is the voltage sensor which produces the voltage in the ABC coordinate. This once again need to be transformed into the alpha beta coordinates and again to the DQ coordinates. Why to alpha beta? Because we need to work with the PLL. PLL is the phase locked loop which synchronizes the grid voltage, which synchronizes this inverter side voltage with the grid voltage and produces the omega triangular frequency. Now, this alpha beta coordinate is again transformed into the DQ coordinates, which produces D axis voltage and Q axis voltage. It is easier to work with the DC quantities, or rather, our controller is compatible with the DC quantities. That is why we have used here ABC to DQ0 coordinate transformation, so that it will be easier for our controller to work with the DC values. Now, this is our coming back to this current sensor. These are our ID and IQ values, which are compared with the reference values. See here ID star and IQ star. The difference of this ID reference and ID goes through a controller. Here we can use the PI controller also, or any of the control strategies. I have used the fuzzy logic controller here. Now IQ reference is generally set to 0 here because so as to achieve the unity power factor. Now this is fuzzy logic. 2 fuzzy logic controllers are used. One is for the D axis, another one is for the Q axis. For the D axis, to comparison between the D axis and with its reference value. For the Q axis, we need to set the reference value to 0 so as to achieve the unity power factor. That is why 2 fuzzy logic controllers are used here. Many of the research papers also use PI controller here. Then, which is added to the D axis voltage and the Q axis voltage. Then it goes to the UD and UQ, which needs are these voltages are once again in the DQ coordinate, but our inverter is a 3-phase inverter. Therefore, This DQ coordinate needs to be transformed to the ABC coordinate, which again needs this omega t value, which passes through a PWM, then pulse width modulation, which goes through the, which controls the pulses to the inverter. Now, fuzzy logic controller receives two inputs. One is error and the change in error. Coming to the controller part, error and the change in error are the two inputs used, and our output is the duty cycle. This error equation to compute error is E of k is IDQ. It is the difference between reference value and the measured quantity. So D and Q I have used in one equation. Once you can use for the D axis, next time you can use it for the Q axis. For the simplification of understanding, I have put it in the one D comma Q. That is, error is the difference between the D axis reference at kth sample minus D axis value of the current measured. Similarly, again, the error is the Q axis of the reference quantity at the kth sample minus Q axis of the measured current at the kth sample. Then CHE represents the change in error, which is the difference of error and its previous value. This error and its previous value. Now control out duty cycle is again its previous value plus change in duty cycle. Then the fuzzy logic controller is implemented in the inverter control strategy. These are the membership functions of input. E error and CHE is the change in error. These are called as the membership functions. NL stands for negative large. NM stands for negative medium. NS stands for negative small. ZE stands for zero error. PS stands for positive small. PM is positive medium. PL stands for positive large value. And it is arranged in the range of -1 to +1, passes through 0. These are the membership functions. These same membership functions are used for the input, as well as 7 membership functions are used for the change in error and change in error. Similarly, 7 membership functions are used for the output control. Excuse me. Hello? हाँ हाँ ठीक ଅଛି ठीक ଅଛି हाँ 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 Sorry for the interruption. We have used 7 membership functions here: negative large, negative medium, negative small, and the zero error at position 0. Then positive small, positive medium, and positive large. These are the 7 membership functions for the input, error and change in error, as well as for the output. So the same thing is written here. Now the controller's domain for the membership functions are -1 to +1 for error and change in error, as well as for the output. Now this is a table used. Implementation of fuzzy logic controller in the inverter control says that error is E, change in error is this side, is this column is error. Negative large, negative medium, negative small, zero error, positive small, positive medium, positive large. These are the errors. These are the once again similarly change in errors. As we have 7 membership functions for the change in error, as well as 7 membership functions for the error, therefore 49 rules are formed out of this one. Now, it is a fuzzy logic controller is an aggregation of if and then rules. So we can have one example here. If error is negative large and change in error is negative large, then our output duty cycle will be negative large. Similarly, we can take for any value if the error is negative small and the change in error is negative small, we have the duty cycle as negative small. Or when the error is zero error and the change in error is negative small, we have negative small as the duty cycle. So this fuzzy logic controller is formed on the experience basis and is a trial and error method. We need to go on trialing till we achieve the proper performance criteria, whatever we have set for the settling time or rise time, overshoot these all performances till it satisfies. We need to um, go trial and error, go on changing this to the table for, and accordingly we'll get the output. Now coming to the results and discussions. Now design of a PV system connected to DC bus, we can see that for different values of irradiances, as the irradiance changing, I'll show you in the simulation diagram also, as the value of the irradiance changes, see different values of irradiance is changing in steps. Okay. When the irradiance is changing, our output power is also changing. This is blue line is the irradiance and red is the output power. As the irradiance changes, output power also synchronizes and synchronizingly changes with that one. I have taken 0 to 10 seconds simulation as the simulation time. You can take about 5 time or 5 seconds or 15 seconds also depending on the speed of your system. Then DC bus voltage, you see, whenever we change the irradiance at any position, see this blue line is the change in the irradiance. It is changing at different places. For any change of the irradiance, our DC bus voltage is constant, which is maintained at 70 volt. This I'll show you with the from the simulation. It is always maintained at the 70 volt, irrespective of the change in the irradiance. Then battery current. Battery current also, see, when our irradiance is 1000 watt per meter square, then our battery will go on charging. Okay. When it charges, it will receive, see near this 1000 watt per meter square. When the battery charges, battery current will go as negative. And for these low values of irradiance, you see, initially we have started with very low values. This is 500. So around 300 to 400, I think this value. For 400 value, the battery needs to be charged. It doesn't store energy at this point of time. So when the battery is charging, you see positive value of current is established. Similarly, for different values of irradiances, as the irradiance changes, our battery goes on charging. And when the irradiance goes to around 1000 watt per meter square, you see when it is 1000 watt per meter square, then the battery discharges. Sorry, battery is charging. At this point, battery is discharging. Now, DC bus voltage, we have seen this one, 70 voltage, it needs to be kept constant. Now, this is the variation in the battery voltage when it is charging and when it is discharging. When it is charging, battery voltage goes on increasing. And then when it is discharging, battery voltage goes on decreasing. A design of a PV system connected to DC bus. This is state of charge of the battery for different irradiance conditions. Then this is PV power and battery power. So this is our PV power. As the PV power goes on increasing, that is at any point of time, the load demand needs to be satisfied by the PV and the battery power summation. So at any point, this load demand is satisfied by the PV and the battery power balance. You can see it from the simulation diagrams. Then connected to the AC grid. When it is connected to the AC grid, Of the fuzzy logic controller, there we have used time versus voltage plot when we have taken minus 500 to 500 value. This is the peak value of the voltage and this is the peak value of the current. Peak value of the current is around 103 ampere. This is grid current at different outputs. Grid connected current accurately follows the grid voltage in frequency and phase, achieving unity power factor grid connected operation. See, you can see from this figure, this is our voltage curve in a single phase. This is our three-phase curve. This is our three-phase curve of current, and this is for the voltage. We have taken through one demux and found out the single phase voltage and per phase current. This is VA and this we can say as IA, or let it be in any phase. See, the phase difference between this voltage and current is zero, which says that it is operated at unity power factor operation. That is, voltage is synchronized with the phase. This curve represents grid voltage and active current at output. Now the current and time plot is taken to just show that red curve is the reference value of the current. Our current accurately tracks this reference value of 103 peak value. 103 is the peak value of current. You can see from this reference value of red curve, our current per phase accurately tracks the peak value of the current of 103 ampere. It is shown in the simulations. Then is the active power injected into the grid, and this is the reactive power injected into the grid. Now, active power is, we can see that we have taken a 50 kilowatt of PV system. Active power reaches at 50 kilowatt with a little bit of delay. And our reactive power, as we have kept the reactive reference current value to zero, therefore reactive power injected into the grid is zero. We have injected zero reactive power into the grid, therefore this voltage and current are synchronized in phase with each other to deliver the unity power factor operation. After this conclusion, this is my conclusion, but I will present the simulation also. Now, in this conclusion, we have modeled this DC side and the AC side of the bidirectional converter with the particles of optimization and MPPT controller. Then the simulations suggested controller stabilizes the DC bus voltage of 70 volt. Then fuzzy logic technique is implemented for the control of the inverter connected to the grid. Then we have seen that the waveforms accurately follow the reference value and promptly reaches to the steady state value. These are my references. Now, let us go to this simulation. This is power GUI block. This is
945, 46.
this is the PV array with 1000 watt per meter square and 25 degrees centigrade.
ஆமா ஆமா
See, we can
ஓரளவுக்குதான். அப்புறம் ஒரு முகத்தை பாப்பீங்க. நீ என்ன பண்ண ரசிகர்களுக்கு என்ன பண்ண அதுக்கு
5 parallel strings
என்ன
are
உங்களுக்கு
taken.
எனக்கு என்ன புரியலன்னா தூங்குறதுக்குன்னா அதுக்கு நீங்க வந்து அதுக்குள்ள
Please
வயசுக்கிட்டு
mute your
உடம்பு
mic.
முடியல ஏதாவது பரவாயில்ல எல்லா டைம்
Could you please mute your mic? 5 parallel strings are taken and one series connected string is taken. Maximum power is 213 watt. So when we multiply number of parallel strings into number of series strings multiplied by 213, it comes around 1065 watt. Therefore, you might be seeing in the simulation output that the output is around reaches 1065 watts. But on the average, we can use it for the 1000 watt PV system. Cells per module are 60. Then see open circuit voltage 36.3. You see short circuit current is 7.84 ampere. Voltage at the maximum power point is 29. Current the maximum power point is 7.35. We can plot a different irradiances and see that. See at different irradiances, it is 1000 watt per meter square. This is 500 watt per meter square, and this is 300 watt per meter square. Similarly, this is voltage and power curve. This is voltage and current curve. Voltage and power curve reaches 1000 watt per meter square. See, X is says that 29. So X-axis represents voltage. It means at the maximum power point, voltage is 29 volt. Same we can see from this graph. At the maximum voltage and maximum power point is 29 volt. Similarly, y-axis 1065.75. That is maximum power is 1065. We can use it for 1000 watt or 1 kilowatt. Then at 500 watt per meter square at different values of irradiance also see our voltage is changing and the power is also changing. See at 300 watt per meter square, power is 321 it displays and voltage is 29.14. Similarly, at 500 watt per meter square, we can see that x-axis and y-axis value of 539 watts. So as the irradiance goes on changing or increasing, our output power goes on increasing. Similarly, this is our current and voltage curve. This we can see that at maximum power point voltage is 29 volt and y-axis represents 36 volt. See open circuit voltage of 36.75. We can see from here the current at maximum power point is 7.35 multiplied by 5 will get you this value. 7.35 multiplied by 5 will get you 36.75 ampere at maximum power point tracking of 1000 watt per meter square. Similarly, different values at 500 watt per meter square and 300 watt per meter square. We can plot it for different values of temperature as well. Now, this is, we have considered the temperature at 25 degrees centigrade and current and irradiance as 1000 watt per meter square. IRR represents the irradiance value. Okay. Then this is our, this represents our VPV and IPV. This is called as bus selector. Then which goes to the MPPT algorithm. See VPB and IPB. This represents VPB. This is IPB. When it is given, this point is VPB. This point is IPV. When they are multiplied, it gives the PV power. PPV represents the PV power. again voltage, PV current, and it's the time is the step. But it is given to MPPT control algorithm. It gives the duty cycle. This is a perturb and observe method used here. We can use different other algorithm also. A duty function is MPPT control of V, I, and delta E. Initial duty I have taken as 0.4. Minimum duty I have taken as 0.1 and maximum is 0.9. Then these all MPPT algorithms. Power is voltage multiplied by current. The dV and dP is represented, duty is represented, then the if loop, if else loop. If dV less than 0, then duty is duty old plus delta D. Otherwise, duty equal to duty old minus delta D. And then the previous values are established, which passes through a PWM generator. See, we have taken 5000 hertz or 5 kilohertz as the switching frequency, and sample time is 10 e to the power minus c. You can see here the sample time of 10 e to the power minus 6, which provides the pulses to the boost converter. This is mentioned as S boost. That is, it gives the pulses to the switch of the boost converter. Now, this is the boost converter. You can see the ratings, but voltage needs to be kept constant. Therefore, a high value of capacitor is around 1000 microfarad is used, and resistance value is very small. These are the parasitics. You can consider only the value of the capacitor and do your simulation also. Then these are the inductance values, 5e minus 3, 5 millihenry, and 0.1 as the resistance. Then this is the switch, this is the diode, and this is the output capacitor of 3300 microfarad, having a parasitic resistance, which is given to a load of 6 ohms. Then this is a current measurement scheme. This goes to a boost converter, I boost, to see the result. Now this is a voltage is measured. It is called as the V bus. Now, as I told you at that point, 70 volt has not come randomly. Rather, we have to see at this point what is the bus voltage. Whatever bus voltage comes, accordingly, we need to give the reference value here. See, 70 volt. Initially, I calculated the bus, or I have seen the bus value bus voltage coming as 70 volt. Then we have taken 70 volt as the reference value. Then this is the bidirectional converter. Bidirectional converter, it is 1000 microfarad. Then these are the two switches. It can work either as a buck converter or boost converter. This is the inductance value. Then S1 and S2 are the switches. This is the battery. Battery is say 24 ampere hour. Nominal voltage is 24. Rated capacity is 50 and initial state of charge is 45. Battery response time is 1 second. And battery type is lithium ion. Then this is a selector which gives you the SOC value, state of charge. VB represents the battery voltage, IB represents the battery current. Now, when this VB and IB are multiplied, it produces the battery power. So we have to see that battery power and the PV power at any point of time matches with the load demand. Now, 70 volt is the taken as the reference value of the V reference. The V reference and V bus are compared. Rather, V bus voltage is compared with the 70 volt. The difference is passed through a PI controller. See, the PI controller has proportional and the integral KP and KI values. then it goes to it produces a reference value of the battery current, which we can see through our display also. Then this battery reference value of current is compared with the battery current, which goes through a PI controller again, the KP and KI values. This produces the duty cycle of the battery. Now the duty cycle of the battery once again passes through a PWM generator, DC to DC generator of 5000 Hz and 10E minus 6. E minus 6 is the sample time. Okay. Then S1 and S2. There in the diagram, I had mentioned Q1 and Q2 as the two switches. Same mentioned in the simulation diagram as S1 and S2. That is duty cycle. If it goes to the switch 1, if S1 is not operated, then it goes to the S2 switch to operate the bidirectional converter as a buck converter or boost converter.
Excuse me,
Then these
ma'am.
are the
Sorry to interrupt you. I mean, I have a question that how do we select the KP and KI values? Can you please elaborate?
there are different algorithms used or different optimization techniques. Basically, it is a trial and error method. So we can go on trying the values of KP and KI, and we can see that till our bus voltage reaches the 70 volt. Whenever the bus volt reaches 70 volt, we stick to that KP and KI values. But that KP and KI values can be found out through particle swarm optimization is a method I have used to find out. And different optimization techniques are mentioned in the literature to find out the KP and KI values.
Okay, ma'am. Can we implement here that technique? Like
Oh, obviously, you have to implement. There, like I have used the particle swarm optimization to find out the KP and KI values. Otherwise, you will go on putting trial and error method, which is a very long, lengthy process, and you may not get the accurate result also. That is why in each and every controller, whenever you are using, you need to have a optimization technique. So when we are studying the controller, we need to study about the optimization technique besides that one. Okay.
okay, ma'am. Actually, if we want to implement the optimization technique for designing that controller, so where can we? I mean, for simulation, can you show where we have to put that algorithm part? I did not have any idea, so
I'll tell you. See, this is the PI controller.
okay, ma'am.
ITAE, have you heard of ITAE? Index, different indexes used, ISE, ITAE indexes used. And ITAE, IAE and ISE, integral square error, integral time absolute error, ITAE. These all are the parameters used to find out when these parameters are minimized. At that point, whatever KPKI values PSO algorithm will give is the final one. See, at this PI controller, when we are using PSO algorithm, before this PI controller, at this point, can you see the pointer? At this point, and at this
Yes, ma'am.
point, we can use a ITAE index or integral square error or any index. I used ITAE index to find out when it is minimized, when the ITAE, and it is represented in the PSO algorithm. When the ITAE is a minimum, at that point, the optimization technique will automatically give you the KP and KI values. Okay, this is before this PI control loop, it goes to a ITAE block, and which is used in the optimization technique. The another program have you seen here? It is not a simulation now. Remember PSO. PSO you need to write down here. Here, okay. PSO code you need to write down here, and you need to call it for the simulation. Okay. Now
Okay, ma'am.
this, okay, this irradiance and bus voltage, reference voltage, Then state of charge, and this diagram is also mentioned in the different literatures ITAE, you can find out. Then a
Okay,
state
madam.
of
Thank you,
charge,
madam.
battery reference, BB voltage, PV voltage. We can see when it runs. Now, while studying for the controller, we need to study for the optimization technique also simultaneously to find out the parameters of the any of the controllers. Saying fuzzy logic also is a trial and error method. To find out its parameter or membership functions, we need to have different optimization techniques. Therefore, I have written in my objective that a suitable control strategy along with a suitable optimization technique needs to be developed.
All the ladies of the house will prepare the cover and they will get it to the center of the house, maybe center of the village, and place them in the place, open door, and all of them will do dance rolling around the customer. And then they perform puja, distribute the father, and take them.
See, at 1000 watt per meter square, this is our irradiance, 1000 watt per meter square. At this, in spite of battery charging or discharging at any point of time, the battery voltage is mentioned at 70 volt. And the state of charge is, say, it is increasing. Because the battery is discharging at this point, so state of charge is increasing. Now, battery current, you can see that blue line is the battery current, red line is the reference value. See, the battery current coincides with the reference value of the battery current. Now, when the battery is charging at 1000 watt per meter square, the current is negative. This I can show you in the individual. See, battery is current is below 0. Okay, so battery current is charging, battery is charging, which says that the current value goes negative. Similarly, voltage goes on increasing when the battery goes on charging. This is VB states that battery voltage, see, 20 more than 25 volt, it has charged. And this is our PV power, 1000 watt. See, around 1065 it is, because 213.15 something we have taken and 5 multiplied by 1 series and parallel strings. This we can see in the individual plot also. The irradiance and PV power, the irradiance and PV power. It shows the curve more clearly. Irradiance is 1000 watt per meter square and PV power is 1065 around. Then battery current and a reference value. It tracks the battery current and the reference value, say it is below 0. So we know that our battery is charging. So when it is charging, current goes negative. Then you see battery voltage is increasing. You see this one is the marks we have used between bus voltage and reference voltage. Reference voltage is 70 volt. Red line says that it is reference voltage. Blue line is our bus voltage of 70 volt. Then state of charge. When the battery is charging, say state of charge is increasing. Then battery voltage, anyhow, I have seen here. So I have shown you here battery voltage. Voltage is increasing when the battery is charging. Now, this is PV battery power and PV power. You can see battery power and PV power. This is by mistake written as bus voltage, okay? Because I have not changed here. Anyhow, I have to run it once again, otherwise it will not show. It is battery power and this is PV power. Okay. While when I run it for the second time, you can see that it changes. Okay. Now this is PV power is 1065 and see battery power at any point of time when your battery power and PV power combinedly should satisfy our load demand. Then I can show you. See, look at this one. This is a different values of irradiance that we can delete now. At different changing values of irradiance. Whatever we have seen now is particular value of 1000 watt per meter square. Okay. Now, okay, 1 minute. I can show it at 300 watt per meter square also. That is when the battery is discharging. You had seen that at 1000 watt per meter square, battery was charging. And when the irradiance is very less, around 300 watt per meter square, the battery will discharge. So here we can run it again.
Ma'am, the radiation profile you have choose is the duration is in seconds or in hours actually?
Seconds, obviously. Because see, our simulation is running for 15 seconds.
All right. So actually the battery, I have observed that the battery, actual battery or in the simulator, the battery actually takes longer time to charge and discharge. So that's why I'm asking that how it is matching with the.
It doesn't follow immediately. That is why the controller needs to be designed properly and accurately. Then only it will follow with the immediate change. You can see from this, when I'll show you with this one signal generator, you can see that with the immediate change of the irradiances, our controller accurately follows this one because the controller parameters KP and KI are designed properly. So in this one, you can see this one. Yeah. 300 watt per meter square is our irradiance. When it is in spite of the irradiance at 300 watt per meter square, our DC bus voltage is always kept constant at 70 volt. Now, you can see from this curve, this is state of charge is decreasing. Okay, that is battery is discharging. When we had seen at 1000 watt per meter square, the battery was charging. That is why the state of charge was increasing. But at 300 watt per meter square, the battery is discharging because it is not sufficient for the load demand. So this is state of charge. Now again, see this battery current IB represented by the blue line is the battery current. IB reference is the red curve. Both are matched. That is battery current matches with the reference value of the current generated from the PI controller of the voltage control loop. Okay, we had seen the voltage control loop. I'll show you again. Do you remember? In this slide, in this slide, you can see that VDC reference and VDC This VDC reference is 70 volt. When it is compared with the DC bus voltage, it passes through a PI controller, which produces a reference value of the battery current. Now, this is compared with the measured value of the battery current. This is the external voltage control loop. This is the internal PI control loop. Now, this shows that the battery current matches with the battery reference value. Then this is the VB, that is battery voltage. Battery voltage, see, when the irradiance is very less, around 3000 watt per meter square, which is not sufficient to charge, rather the battery discharges. The irradiance is not sufficient to provide the load demand, therefore the battery discharges. So the voltage goes on decreasing. When it was 1000 watt per meter square, you had seen that the battery voltage was increasing because the battery was charging. Now at 300 watt per meter square, the battery voltage is decreasing. That is why it is battery is charging. Therefore, voltage is battery is discharging. 300 watt per meter square, battery is discharging. That is why battery voltage is decreasing. Then it is PV power. PV power, see, at 300 watt per meter square, it goes around 300 watts. When it was irradiance was 1000 watt per meter square, your PV power was 1065 around. Now, when we have changed the irradiance to 300 watt per meter square, our PV power also changed to 300 watt around. Now, you can see from this plots also, individual plots. Around 300 watt per meter square is mentioned. Then IB and IV reference are also matched with each other. Individual curves we can see. Then bus voltage matches with the reference voltage of 70 volt. This 70 volt is the reference value irrespective of any irradiance value. Let it be 1000, let it be 300, let it be 500 watt per meter square. Our DC bus voltage will always remain constant at 70 volt, which is the design of the bidirectional converter control strategy. Then state of charge. See, state of charge is decreasing because our battery is discharging. Then the battery voltage. When the battery is discharging, our battery voltage is decreasing also. You have seen in the 1000, it was increasing. Now PV power and battery power. Even if the load is 300 watt per meter square, see the PV power. See, I have changed their PV battery power. This is pink line is PV power. PV power is around 300 watt. Battery power both combinedly, as the PV is not sufficient to provide the load demand, therefore the battery discharges and satisfies the load demand at any point of time. Now, we can use this and we can see it at different irradiance values also. Say like we have used here the irradiance of 700 watt per meter square. You can see at a time from this curve, see 700 watt per meter square is the irradiance value. In spite of the change in irradiance to 700 watt per meter square, our DC bus voltage is maintained constant at 70 volt only, which lies in the control strategy or the design of the bidirectional converter controller. And the state of charge, as the PV power is sufficient at this point, battery is discharging, so state of charge is decreasing. And you can see the battery current matches the reference value at any point of time. You can see that this is battery current is having positive value, that is the battery is charging. Battery is discharging, sorry. The battery is discharging, that is why above zero. You can see this one. At 700 watt per meter square, the PV power is sufficient. That is why the battery is discharging. That is why current once again goes positive. While for the lower values of the irradiance around 300, 400, we have seen that the battery charges and the battery current goes negative. Similarly, battery voltage. See, at 700 watt per meter square, battery is discharging. The battery voltage is also decreasing from the initial value of 25.78 around. And PV power is, we can see from this graph, 750 with around 740, 50, because 213 we have taken multiplied by 5. Okay. Now, similarly, we can see for the individual curves also, but as you have understood, I think no need to show those changing irradiance values. Then directly we can go for this changing irradiance in steps. We can first see from this changing. So this is mentioned in seconds: 0 second, 2 second, 4, 6, 8, 9, 10, 12, 13, 14. I have taken up to 14 seconds. Depending on that, irradiance value is also changing: 400, 500, 600. It goes to maximum of 1000. Then once again, irradiance decreases: 900, 800, 700. Sample time is as mentioned in the power GUI. So when this step value of change in irradiance occurs, how does our controller accurately follow the change in irradiance for the battery charging and discharging? We can see. See, you can see from the display also, it is continuously changing PV power when the irradiance changes. You can see at this display, and wherever display is there, you can see that it continuously changes. These displays, see, battery reference values and this out of the PI controller, it continuously changes. Now, if we connect one integral absolute time error ITI index for the PSO and connect one display, we can see that the ITI error also continuously decreases, and when it reaches to 0, at that point, we can take the values of the KP and KI. It will give it in a tabular form directly. And then you see, initially we had taken 400, then 500. We have seen this one 400, then 500, 600, 700, and reaches to 1000 watt per meter square. See from this one. say 400, then 500, 600, 700, 800, 900, then 1000. Then irradiance also decreases. As the irradiance decreases, similarly, we obtain our irradiance value as it goes on increasing, reaches 1000, then decreases. When it reaches 1000 watt per meter square, you see that this PV power also reaches 1000 watt per meter square. PV power also at 400, 500, 600, 800, it also continuously changes. See this one continuously changing and goes on decreasing after 1000 watt per meter square PV power. In spite of the change in the irradiance from 400 to 1000 again to 700 watt per meter square, you can see that the DC bus voltage is maintained constant at 70 volt. V bus is the blue line, V bus reference is the 70 volt. 70 volt, you can see that the bus voltage correctly tracks the reference voltage. Then state of charge is also changing accordingly. See at that point, battery is charging. So state of charge is decreasing. Similarly, as it goes around 1000 watt per meter square, battery discharges. So this gives rise to a smooth curve. But the actual variations we have seen in the by considering each irradiance individually. As our irradiance continuously changes here, that is why we have got a smooth curve here. But we have seen from the earlier irradiance value while considering each one that it is either decreasing or increasing. Then the battery current tracks the reference value properly. The red is the battery reference value, blue line is the battery current. And each value say 400 watt per meter square.
Excuse
Battery,
me, ma'am. Actually, ma'am, when the this is your irradiance is increasing, battery will charge or discharge? It will charge, na battery.
See, when irradiance is increasing, if it is not sufficient, how can the battery charge? At 400 and 500, so irradiance is not sufficient to charge the battery, to sufficient to provide the load demand only. How can it charge the battery?
Okay, ma'am.
It will charge
at 1000 at 1000 watt per meter square irradiance, battery will charge or discharge? That I want to know.
At 1000, battery will charge because it is sufficient. We have seen now in the earlier curves.
Okay, that's
we
right.
have seen in individual curves, na?
While speaking, you are telling something opposite.
Oh,
that's why.
maybe some I have explained different irradiance values, na? Sometimes by mistake.
Okay.
But as say
So,
400, 500. Okay.
At a higher irradiance, battery will charge.
Obviously, when it is sufficient to provide the load demand, where the rest of the energy will go, obviously it will charge the battery. We have seen it from the individual curves. That is why I had shown you the individual curves earlier. And because it is just a smooth curve, it will not be properly identified from this one. That is why we have seen the each value of irradiance earlier. This complete one is to so that it tracks properly. Similarly, this battery voltage and this PV power also. We can see from this curve also battery power and PV power. See, at any point of time, the battery power and the PV power combinedly supplies our load demand. And same thing only we can see from this one that it tracks the bus voltage. Over with the simulation. Over with the simulation. Now let's go back to the PPT. Okay. So we have this bidirectional converter explained Q1 and Q2 switches. Q1 and the Q2 are the two switches which operates either as the buck mode or as the boost mode to charge or discharge the battery. This control strategy and the identified, okay. This is our same as control algorithm. This is bidirectional converter. From we started from the system configuration and design. Okay. This was bidirectional converter model. Okay, that's all. If we get any other session, we will try to consider any other PSO algorithm or something. Okay then.
Ma'am,
Okay.
before you end the session, I'm requesting you to just show how to use the ITA block. I did not actually get that point. If you please show the
Okay.
ITA block.
IT block is in different. Okay, I'll try to show you for other one. For this one,
Okay, ma'am, no
maybe
problem.
wait.
Any.
Okay. Okay. Let me show you IT block. This one is an ITI. Before this PI controller, one you can find out this in different literature also. This is ITAE index, integral time absolute error. Okay. This is
Okay, ma'am. That means we have to
okay, absolute value.
code the algorithm.
You have to write the algorithm.
Then workspace.
Yes.
Okay.
Yes. Then this is our absolute value. This is our clock. Decimation, any value we can put. Then this is the integral value, ITAE. Then it will go on decreasing. This is for a different simulation, but before the PI controller. If you have more than one PI controller, you need to add a summing block there and add the absolute values. Okay, add the absolute values, then it will show you. Okay.
And same way we can use the method for designing controller for inverter also. Like for
inverter
AC
control
side.
also you can use any control. For any controller you need to use an optimization technique. Let it be PSO or let it be Anderson-Hoff or artificial B colony. Different optimization techniques are used. Any controller, any optimization technique you can use to find out the
cannot do by
parameter.
simple mathematical operation. We cannot do like if
yes,
we
you
find
can
out
do
the
Bode
transfer
plot.
function.
Yes, you can do it. Bode plot you can find out, and you can find out the KPI values also. Okay, basically it is a trial and error method. Okay, any more questions?
Thank you.
Okay.
Ma'am, in these discrete time simulations, ma'am, in these discrete time simulations, how do you set the sample time for the inner current control loop and the outer voltage control loop?
Depending on the switching frequency, we need to set. Okay, inner control loop should work very fast actually. Outer control loop should work after the inner control loop has worked. So we can sometimes the same sample time also works. As I have seen you here. And this one, same power GUI working sample time have works. But different research papers, sometimes they have taken different times also. Okay. Any more questions?
I have last question, ma'am. That in the fuzzy logic control you have shown the block diagram. There were one by Z block, and after that there was a FLC like fuzzy logic controller. So if we want to implement that in Simulink, so we have to do the logic part in which section?
No,
And
1 by
what
Z
does the
is
1
the
by Z block mean?
1 by Z represents the delay time only. Okay.
Delay
But the
time.
controller, it is 1 by Z is very simple delay time. But we need to produce the accurate rules actually. 1 by Z is simple delay time given. Okay. These membership functions and forming the rules are the core strategy. Once we form the core rules properly, within bounds, it will work. Okay, for any of the
For that
controllers.
also,
And it is
for
a
that also
different
we
dot
have
F.
to,
Okay.
yes. Please continue.
And it is a dot FIS file we need to import. We need to, and it's a online available in the MATLAB dot FIS file. We need to make it to arrange the membership functions accordingly and put the values. Membership functions we have seen now here. These membership functions.
Yes.
These membership functions we can find out through our that .fis file. We need to form it actually. Different negative large, negative medium, negative small values. We need to form it properly. Okay, .fis file we need to make. Then their control strategy we need to make. Then the fuzzy logic control block will also work.
Ma'am, since I think you have got a lot of time now left in your session, can you please explain properly this fuzzy logic control? Is it
Yes,
possible?
Okay. I have different, I'll just try to show you, I have different, let me try. Fuzzy logic, where I have tried. See, this is PO perturb and observe MPPT curve. We have used the fuzzy logic algorithm here. This is fuzzy logic dot FIS file we need to perform. And this is perturb and observe. These are the memory blocks. These all are the memory blocks we need to find out. And then which is given. So these are basically the error and the change in error blocks. So obviously for the error and the change in error, it should be compared with the previous values. See in this one, 1 minute. These equations, error and the change in error, the D and Q axis kth sample must be subtracted with the D and Q axis kth sample. So, and it will take the K minus 1 is the previous value. Now for the previous value, we have used these blocks. Okay. We have used this memory blocks which stores and dV value, change in the voltage as we know from the incremental constants, change in dV value, change in dP value, those all are dP by dV goes through a memory once again, error and the change in error. This is our error. Difference of this one and the change in error direct goes to the fuzzy logic block .fis file which passes through the memory, and this is our saturation upper and lower limits which goes through a switching frequency and sample time, then which operates our boost converter here. Okay, is it okay?
Okay. Little more about the membership function.
Membership functions. See, this is our fuzzy logic. When you type fuzzy in the window, it will give you this kind. Okay. This is our input and this is our
Ma'am,
output.
your screen is not
Now,
visible actually.
not
Video
visible.
is not visible, ma'am.
Okay, okay. Let me see. Is it not visible?
No, ma'am.
Okay,
No, ma'am.
okay.
It's not visible.
1 minute. Visible? Is it
Yes, now
visible?
visible.
Yes, visible. Visible.
Yes,
Visible.
Okay.
yes. The screen is
Okay,
visible.
okay. Now, when we write down fuzzy here, see, it will get you this fuzzy logic. .fis file you need to store. Now, you need to add variables to input or output. We have considered two membership, two input and change in error. So we can use here, see, we can use here ERR, error, and this one as change in error. See, input membership functions, we can, input variables, we have changed their names. Similarly, the output name is, we can use as the duty cycle. See, it is duty is written here. And Mamdani fuzzy, Mamdani fuzzy I have used. You can use a different fuzzy logic, Tika Suzino fuzzy also you can use. Then for the error, see, these all are the membership functions by default given. Membership function 1, 2, and 3. I can change the membership function values. Okay. I can change the membership function values, add membership function. We'll add a different membership function. We can add remove selected membership function. It will remove the selected membership. Whichever you select, it will delete that membership function. See, edit, remove selected membership function. We delete this one all. Then rules, similarly add membership function will add. Now this is the trapezoidal membership function. If I say trapezoidal membership function, it will add a trapezoidal membership function also. Different kinds of membership functions you can add from this graph plot. See, Gaussian membership function, these all are having different curves. Similarly, for change in error also, see, by default it is given.
Hello?
And we can see,
అది లాస్ట్ సెమ్ ఏడిఎస్కి మీరే కదా సార్ క్లాస్ కోఆర్డినేటర్ సార్ అది నాకు కొంచెం రిజల్ట్ ఇవ్వగలరా ఏమన్నా అంటే సబ్జెక్ట్ది
ma'am, it is not audible. What are you saying?
మీటింగ్ జరుగుతుందా సార్
Ma'am, what are you saying?
అదే సార్ ఆవిడ ఫోన్ లిఫ్ట్ చేయట్లా నా దగ్గర నెంబర్ ఏమన్నా డిఫరెంట్గా ఉంది ఓ
See, MF1, it is negative large. If I write down, this will change to negative large. And if I select this one, if I write down negative medium, it will change to negative medium now. So names we have changed accordingly. And similarly for the error also, for the change in error also, Similarly, for the this also membership functions we can change. We can add membership functions, negative medium. Then this one we can select, and this is positive large. Whatever membership. Similarly, I have formed 7 rules, 49 rules out of 7 membership functions for the input and the output. Then okay, then FIS rules. See, we can put when negative large, and this is error. We can remove selected membership functions. Then we can select this one and give this name as negative large. This name as say here positive large. Then we can see the rules. Edit rules, see negative large. When error is negative large, positive is negative large, and duty is 1 minute. While set the duty also. Duty also for this one. Negative large, negative medium, positive large. Okay. Now we can see the rules. When error is negative large, change in error is negative large, change in negative large, duty is negative large. If I say, then the rule will be introduced. Similarly, we can form the 49 rules, which is shown in this table. And we need to save the .fis file. Okay. These are the 49 rules formed accordingly. For it is negative large, then the duty cycle is negative large. When it is negative medium, error is negative medium, change in error is negative medium, it is negative medium. When the error is negative small, change in error is negative medium, duty cycle is negative medium. We have seen accordingly in this, adjusted the rules. Okay.
We can change the rule depending upon the application.
Yes. It entirely depends on the who is setting there the rules. Okay, you need to identify the rules. You need to change the rules, and at that particular value, you need to import the .fis file and see that what are the parameters. Okay, and what are the overshoot, undershoot, whatever you can plot and see, or whether it reaches the particular voltage level or not. You can see.
Okay, and after membership function, we in the Simulink we have to search for fuzzy block, or I mean for importing the
No.
FIS
It
file.
will automatically, if you write down their fuzzy na in MATLAB, it will automatically
Yes.
see. I have declared. If you write down in the Simulink model fuzzy na, it will automatically put you that block fuzzy. You need to put the name of the file only, same whatever we have designed na, the rule base.
Yes.
You need to put the value only. Blank model. You need to put the value of the controller and the .fis file. You need to import it. It will automatically give you the fuzzy block. It's fit in the MATLAB. You need to set the rules, that's all, and the membership functions. And it doesn't depend on the mathematical model, so it is very easy, not easy, rather it's an efficient method. the fuzzy logic control will directly give you this one. You need to only put the name, whatever you have stored there in a dc.fis file. Whatever name you
Okay,
have stored there, this .fis file should be same, then it will work.
okay, got it.
Okay, ठीक है.
Okay, thank you, ma'am.
Okay. Thank you all for
Thank
your
you, ma'am.
patience hearing. Okay, thank you all. So I'll disconnect now. Thank you all.
Thank you. Yes, thank you for that very good session. Thank you, Pranati madam. I hope the participants also get a lot of idea how to design the fuzzy logic controllers and how to implement them for microgrid applications as well as some interconnected systems. Okay, I hope you will get some hands-on experience. Okay, thank you all of you. So next session will be there. It will be coming soon. Okay, maybe 11 it will be start. Thank you.
Thank you all.
Thank you, sir.